Thanks, Emil, for the introduction and for inviting me to give this seminar. Yeah, the title of my talk today is Urban Air Mobility and AI-Assisted Handover Management for Unmanned Aerial Vehicles. I have divided my talk into two parts. In the first part, I will talk about urban air mobility, the definition of it, the use cases. I will give some estimations and projections for the future, and also how cellular networks can be utilized in this specific use case, and also in unmanned traffic management. In the second part, I will be mostly focusing on our published work, which is the AI-assisted handover and resource management for cellular-connected drones. In this case, I will provide some challenges of providing feedback, providing decisions on handover and radio resource management in the sky. Yeah, let me begin with the urban air mobility. Here in this figure, you can see drones transporting some goods and also some flying taxis. And these flying taxis would probably transporting some people. This will be the case how our future cities will look like. And some of the things in this picture are now being realized, but we have still a way to go in order to fully realize such kind of a picture. Why do we need urban air mobility? We need to ask this question because the urbanization and the resulting congestion pushes the limits of our transport systems, and it costs valuable time and money. For example, in the EU only, the traffic congestion costs roughly 100 billion euros per year, and it will cost 300 billion euros per year by 2030. Then why are we depending on only the ground roads? We have sky unoccupied. That's why the urban air mobility tries to add the third dimension to urban transport networks in order to decrease the traffic congestion, decrease the carbon dioxide emissions thanks to these electrical vehicles in the sky. That's why it provides many opportunities. For example, possibilities to create faster, cleaner, and safer environment, transportation systems, and new market opportunities. And also, there are some risks that needs to be solved before getting it fully realized. For example, the safe and secure communication in the secure operation of these vehicles, flying vehicles in the sky is utmost important. Let me briefly summarize what is the history of UAM. Yeah, it can be traced back to 1965, which can be regarded as the first helicopter flight from JFK Airport to Midtown Manhattan. But at that time, this UAM concept is not accepted socially because the helicopters are noisy in the city centers and they are very expensive, so that not much people can afford it. However, in the last 5 years, yeah, we have great advances in drone technology. For example, gyroscope stabilization, simultaneous localization and mapping, and camera systems. But one problem is that we have a battery problem, and at most 40 minutes in the best conditions, we can be up in the sky. And also there is another type of flying vehicles, which are electrical vertical takeoff and landing vehicles, eVTOL in short. And they have efficient energy management systems, some LiDAR technology in order to avoid collisions and detect the collision system, detect the surroundings. That's why, thanks to these advances, we have a new type of aviation we have a new hype in the aviation industry, so that we have more accessible on-demand to air travel and less cost. It will be less costly than the helicopters. And we, thanks to this UAM, we will have multiple use cases enabling multimodal transportation. These transportation can be inter and transportation of people and goods, and also it can be some special mission like air ambulance, supply delivery, and transport of organs. Here you can see some of the examples currently. For example, last mile delivery is being done by some companies. However, there are still some regulatory barriers, and it evolves the logistics as well. And also emergency humanitarian missions can be done with the help of drones. However, again, still regulation is ongoing. And also until 2025, yeah, you can see the trends of the commercial drones that is sold, and also the revenue that it generates. Another participant of the UAM will be the flying taxis, as you can see here, one of the examples of the flying taxis. And it can enable personalized travel in the sky, less traffic, less carbon dioxide emission, because they are electrical vehicles, and it can support the less crowded public transport on the ground. Also, after COVID-19, yeah, there we have different types of use cases. For example, pandemic drones can check and examine the people if they have COVID or not, or yeah, their activity such as breathing rate, heart rate, temperature, and their action. And also in China, for example, drones can be used to distribute medicine, food, and medical equipment during the pandemic. And also agricultural drones can be utilized to disinfect some common areas. When we look into this UAM and its main pillars, yeah, we need to have an integrated approach in order to develop urban air mobility concept. There are three main pillars. One of them is business. And in business aspect, we have different activities such as demand and route planning of the UAM in order to go from one point to another point in the city or intercity. And also revenue model and fare collection models are important in order to make these operations commercially viable. And also there needs to be some operator models and financing models to make them financially viable in the end. However, there are two additional main pillars that are the pillars that the research is being conducted. For example, the first one is the technology. In this aspect, aerial vehicle system architecture, hardware, software development, in-flight, air and ground operation can fall into this category. And also for the infrastructure pillar, yeah, it's mainly focused on integration concepts into city infrastructure, how to integrate the built-in infrastructure into the city infrastructure, and how should we design vertiports so that, yeah, these flying vehicles can land and take off from these vertiports. And also the very important concept is the urban traffic management, so that how can we manage these many flying vehicles in the sky. That's why, yeah, it is a little bit complex puzzle together enable safe, convenient, and economically viable urban air mobility service. Mainly, our focus is the communication in urban traffic management that I will talk about more in the next slide. And in this case, yeah, we will be focusing on more command and control communication beyond visual line of sight and autonomous operation of the flying vehicles and their payload communication, and as well as collision avoidance. Here you can see the current air traffic management. It is mostly centralized. We have air traffic control sending some directions to airplanes so that we can have safe airspace. However, with the introduction of flying vehicles, drones, eVTOLs, yeah, we need more complicated infrastructure, and this is called urban traffic management. It is a framework monitoring and managing unmanned traffic and supporting beyond visual line of sight and autonomous operation of flying vehicles. As you can see, yeah, it is more distributed. There are distributed entities, for example, air service providers providing permission to use the airspace. And also we have some communication network in order to let the drones and the eVTOLs about the situation, and also enabling beyond visual line of sight and autonomous operation, so that, yeah, they can coexist with the other participants of the airspace. Here in this figure, you can see a high-level representation of the potential interaction between the mobile networks and the stakeholders involved in UTM. Here, for the stakeholders, yeah, we can state national authorities, law enforcement, and also air traffic management for the high altitude airspace, and also urban air operators. And also for the drones and the flying vehicles, it is very important that, yeah, we have some external data sources. For example, for the low altitude airspace, weather information is very important in order to safely operate the drones and also the flying taxis. And these stakeholders and external data sources are connected to the UTM system, so that UTM system can send the instructions to the drones and also the flying vehicles through cellular infrastructure. And this cellular infrastructure can use different types of network technologies, and also it can utilize different mobile network operators. In this case, yeah, we may have vehicle-to-ground communication that can be utilized for identification, authentication, secure connection, positioning, and command and control communication for the flying vehicles. And side-to-side link or side link, V2V links, can be used for collision avoidance and also provide identification for the law enforcement. Let's look into the situation today and the future goals. Right now, we are in this phase. Yeah, we have firstly, in level 0, we have no automation. Human pilots are navigating the UAVs or UAVs with visual line of sight operation, so that, yeah, the pilot can see the drone. In the next phase, it is more computer systems doing this, but with human assistance, and also it can also support beyond visual line of sight operation as well. In the later stages, we would like to have more autonomous UAV operation with higher densities, and we will be having, for example, in the next level, we will be having more autonomous beyond visual line of sight operations in low density airspace. And also in the last level, we will have on-demand autonomous operation in dynamic and high density airspace, so that we can have more scalable solutions, so that we can support many flying vehicles in the sky. When it comes to the wireless communication requirements for UTM operations or UAM operations, there are not much constraints, but recently from 3GPP, we can use this 3GPP report in order to adapt the requirements for UTM as well. Here you can see some requirements in terms of data rate, latency, and reliability for the command and control communication and payload communication. Here you can see that for command and control, since we have small data packets, we need to have very low data rate. However, for the payload communication, which can be the communication, mostly video communication from the drone to the base station, it can be up to 15 megabit per second. For the latency, it is very important that the command and control communication has low latency requirements because since the UAVs is operating in the sky, our commands from the ground needs to be reached to the UAVs on time, so that we can avoid the collisions, and also the communication needs to be reliable. These are end-to-end reliability and latency metrics. I need to also point out that. In overall, in our research, we looked into how to utilize cellular networks for UAM wireless connectivity needs. For example, we looked into the problems of remote piloting, command and control requirements to enable beyond visual line of sight communication, beyond visual line of sight remote piloting via terrestrial infrastructure. And also we designed some air-to-air communication models in order to avoid collisions in the sky. And also, we looked into how to manage three-dimensional mobility and handovers, which I will talk about it in the second part of my talk. We have also looked into 3D localization. Right now we are mostly depending on GPS technology, but how can we utilize the ground terrestrial network in order to localize the drones in the sky? Also, drone detection and avoidance is another hot topic in order to detect and avoid any collisions in the sky for UAVs. And also, it is important to monitor the airspace to detect unauthorized drones so that we can avoid any intruders to our airspace. Now, let me go into part 2, which is mostly related to handover management, handover and radio resource management for cellular connected drones. As you can see in the previous slides, drones are utilized in a wide set of use cases. To name a few, area monitoring, surveillance, and delivery drones, delivery use cases are the most important ones. However, in order to fully utilize these use cases, the communication connectivity is really important. And communication connectivity also divided into two, which is, the first one is the command and control communication, so that we can navigate the drone, or we can enable the autonomous operation of the drones, and also the payload communication due to the application. For example, for the surveillance use cases, the drone should send their observations or the video data to the ground center. How can we realize these applications? Recently, the cellular connectivity is studied as the solution because of its ubiquitous coverage. and it provides secure connectivity for the drones, especially for the beyond visual line of sight operations. And there is also a new term in the literature that if the drones are connected to the wireless cellular networks as user equipments, then they are called cellular-connected drones. Here in this 3GPP report, we have a lot of empirical studies for the air-to-ground channel that provides connectivity through LTE. In their report, they also come up with channel models for air-to-ground. This channel model is a bit different because, yeah, we have altitude, we have probability of line of sight depending on the altitude. That's why this proposed air-to-ground channel is altitude dependent. However, in order to support the cellular connectivity of drones, there are some challenges. The interference is the biggest challenge to integrate drones as UAVs in the terrestrial cellular infrastructure. Also, I need to give these definitions because sometimes it may be confusing. The uplink, when we talk about uplink communication, this is the communication from drone to base station, and it can incur significant interference to the terrestrial UAVs. For the downlink communication, it is from base station towards the drone. And in this case, the drone can receive interference from unintended base stations. In this talk, I will be mostly focusing on the uplink communication, which is the communication from drone to base station. Here in this figure, you see the Fresnel zones. For example, as you see, the x-axis, the drone, and the base station has 8 kilometer 2D distance, but still it has line of sight so that it can communicate. But also it can communicate with the other base stations. These ones are these shaded regions also shows the geographical aspects of the terrain. For example, here there are some forests with trees with 50 meters height. However, the terrestrial users in 1.5 meters, yeah, it cannot see this base station. Due to this line of sight condition, different line of sight conditions for the UAVs or drones, the resource provisioning in the sky is a difficult task. What do I mean by that is how should we associate a drone with a ground base station when the drone has line of sight condition with several base stations, and also speed of the drones and large set of line of sight base stations can create excessive number of handovers, as we see in this empirical study. That's why introduction of aerial users into cellular networks needs a revision in the communication technologies. Here you can see some of our analysis of interference on terrestrial communication. Here you can see a partial map of Stockholm. Here this is our drone, and these are the base stations on the ground. For example, in each of these subgraphs, we are increasing the altitude from 1.5 meter to 200 meters. As we increase the altitude of the UAVs, we incur more interference to the ground. That's why it is important to consider interference while integrating the aerial users into the cellular networks, because we should not jeopardize the communication of the terrestrial users as well. The current handover mechanisms designed for terrestrial users, that's why they are mainly focusing on some specific metrics such as receive signal strength. And also the terrestrial users don't have many options to connect to other base stations on the ground. However, since drones are operating in 3D, they have higher number of candidate base station to connect to due to the better line of sight links. And also the 3D movement of UAVs or drones triggers very frequent and unnecessary handover decisions. And we see that it can be up to 5 times more handover decisions at 150 meters altitude than the terrestrial users in LTE network. That's why we need to study the uplink communication of a cellular network that coexists, that provides coexistence between the flying and terrestrial users in order to minimize the interference imposed by the flying users on the terrestrial users, and also to satisfy the flying users' demands in terms of the data rate, for example. And also we need to make good handover decisions so that, yeah, we reduce some ping pong effects or decrease the number of handovers. That's why our focus will be the handover and radio resource management in serving drones in coexistence with terrestrial users. The key performance indicators of our interest will be the interference of drone communications on terrestrial communications, experience delay in drone communications, amount of allocated radio resources to the drones, and rate of handovers. Here is the methodology that we will be following. First, we will be modeling the system and our KPIs. For that one, first we need to look into the air-to-ground channel models, and also we need to model the interference to the terrestrial users because of the communication of drones, and also we need to model the buffer queue size, data and control packets for the delay calculations, and also uplink data rates for the delay. Here, our problem formulation, we will be formulating an optimization problem whose objective function will be the mix of drones, terrestrial, and network KPIs, and our constraints will be related to the handover and radio resource management. In the end, we will be proposing a solver for the problem, and we will be evaluating the performance of the proposed solutions. Here in this study, we have analyzed the received interference from drone communications in the ground base station using cell planning tool. Here we used Momentum Cell Planner with geographical and land use data. We also formulate the handover and radio resource management problem in serving drones and terrestrial users as a machine learning problem. And in this problem, we incorporate the delay in drone communication interference to the terrestrial user in the design of reward function. And also we present a reinforcement learning solution to the problem. What we investigate is that the impact of different system parameters on the handover and radio resource management problem decisions, and we investigate the interplay between the interference and terrestrial users handover overhead, and allocated resources to drones and experience delays. And also, we will be looking at the boundaries of the cells in the sky, handover regions as a function of altitude and speed of the drones. Let's begin with the KPI modeling. Let's focus on the air-to-ground channel model. As I mentioned before, we have altitude-dependent probabilistic line-of-sight channel model, and we have a log normal shadowing and radii block fading for urban environment. I will not go into the details of this air-to-ground channel model, but what we need to know is that it is altitude-dependent and the line-of-sight conditions are probabilistic. And we utilize the 3GPP model, as you can see in this reference. For the buffer Q size, this is the lambda t is the arrival rate to the drone buffer, and this lambda 0 is the arrival rate of data packets which follows the Poisson point process, and also lambda hm is the arrival rate of the control packet. It's again following the Poisson point process. Here in this term captures the total arrival total arrival of control packets during the handover interval, and TH is the handover interval that we have specified. When we looked into this buffer Q size, which is one of our KPIs, the buffer Q size at the next time step will be dependent on the number of data units at the queue at the current time step, and the number of data that has arrived, and also minus the successfully transmitted data units, which is denoted by ST. Let's look into the allocated spectrum and the data rate. The achieved uplink data rate is given by RT, and it is a function of subcarrier bandwidth allocated subset of subcarriers, power allocation vector, and vector of channel gains over the set of allocated subcarriers. Here is the simple Shannon capacity formula, and here you can see the SANR calculations for different subcarriers. And also here, what we need to show is that BT is characterized by an radio resource block allocation indicator function, which is theta LBT. This is 1 if the beat radio resource block of base station L is allocated at time t. It is 0 otherwise. Also, we looked into the interference to neighbor base station, which is another important metric that we need to focus on. It also depends on the path loss and the conditions of the line of sight, and it also depends on the 3D distance between the drone and the L base station. And also we looked into the total interference that is produced by the drone. Here, our HRRM problem is the we need to find the serving base station and the allocated radio and energy resources that minimizes the interference and the interference to the terrestrial users and communication delay of the drones. Yeah, this can be translated into this mathematical optimization problem. In this mathematical optimization problem, we have weighted sum of different KPIs. This is the expected queuing delay. This is the number of allocated radio resource blocks. This is the incurred interference, and this is the handover decision at time t, subject to maximum allowable transmitted power, which is Pmax, and also maximum Q size threshold for the delay. And this third constraint captures that the drones receives service from only one cell. And these Xi's are the scaling coefficients for different KPIs. This problem is a complex and non-convex problem, and the impact of decisions at time t propagates in time and affects different KPIs in later epochs. That's why, yeah, we need to formulate this problem into another problem that long-term benefits can be taken into account. That's why we utilized Q-learning, since it is model-free and explainable, transferable among multiple agents, and can handle problems with stochastic transition and reward without requiring adaptations. For that one, yeah, we define the states as in this form. The altitude, we define the state in this vector, which includes altitude, velocity, current serving base station, buffer queue size, path loss measurement to neighboring base station. Our action space is also the transmit power and the radio resource allocation. The immediate reward function is also the weighted sum of the resource efficiency, low delay efficiency, low interference, and handover regret. As you can see here, it is the inverse of the number of allocated radio resource blocks. For the resource efficiency, it is the inversely proportional to the low delay reward is inversely proportional to the buffer queue size, and also the low interference reward is inversely proportional to the interference. Here, this is how we implement. This is an exemplary network. Here, the terrestrial users and the UAVs are coexisting in the network, and we are given the speed and direction of the UAV, altitude of UAV, base stations, locations, and the parameters for the terrestrial communications. And we also put the as the inputs, we have the coefficients of in the reward function that I have shared previously. We have a central machine learning agent, and our outputs will be the policy on the associated base station and allocated radio resource blocks in the network. Here are some parameters that we have utilized in our simulation study, and as the benchmark, we are utilizing the handover margin if the received power from target base station is 7 dB stronger than the serving base station, then we trigger an handover. Here, in the first simulation result, we focused on the variation of alpha D. Alpha D is the coefficient for the delay. Here in y-axis, you can see the normalized values of KPIs, which are also seen here, which KPIs are we considering. And these results are the results from the benchmark. For example, if we increase the alpha D from 0 to 0.5, yeah, we care more about the handover and interference, and the delay is less tolerable, and we have more handovers triggered. However, in this case, the policy enforces handover to base stations on which the drone experiences less path loss, less interference, and less delay, as you can see in this graph. However, when we increase it further, the number of potential handovers increases only 8%, not much, and also the other for the other KPIs, we don't see any major change. And as we can see here, depending on the coefficients, the RSI-based handover mechanism may perform better. For example, in this case, our benchmark performs better in terms of the queue size. That's why the configuration of these parameters in the reward function is very important. When we change the lambda f, for example, when we increase it from 0 to 0.5, while the other coefficients are 0.5 again, we care more about delay and handover. That's why we are increasing the allocated radio resource block and buffer queue size interference decreases in comparison to slight increase in the handover numbers. If we increase further, we can see that the number of handovers are increasing because the drone switches. Yeah, our UAV, our ML agent fosters more handover decisions. And also we change the alpha H. Alpha H is the coefficient for the handover. As you can see, if we increase it again from 0 to 0.5, we can decrease. We decrease the unnecessary handovers a lot. However, when we increase the number of handovers again, if we increase the coefficient further from 0.5, we experience more delay. More delay because of the interference and as well as the control signaling due to handovers. Here also you can see the case study regarding the rate and position of handovers. Here you can see the heat maps of handover positions. Red dots shows the base station locations, and the lighter blues and yellows shows the higher probability of handovers. For example, when we compare 1 and 2, we have in the same altitude, but the speed increases. When we increase the speed, we have almost cellless connectivity because we have so short time in order to invoke the handover. And also, if we increase the altitude, for example, if we compare 1 and 3, in 1 we have altitude of 50 meters, in 3 we have 250 meters, we have experiencing more handovers because of the line of sight conditions. Yeah, in conclusion, we have studied a learning powered approach for handover and radio resource management. And it is very important to set the appropriate coefficients for the delay and interference, and it should be tuned in order to the aims of yours in your network. And also high speed causes less handover decisions. However, altitude has reverse effects on the number of handovers. As the limitations and the future research directions, we don't have any beamforming approach in this study. And also we have not considered the down tilting of base station antennas. In the future study, we will be also considering in that one. And also we will be considering more number of base stations and radio resources. And also we will be considering the downlink communication, command and control communication in order to have the full picture of this type of scenarios. And also it is important to focus on multi-agent learning in order to scale the proposed solution, so that one direction would be the collaboration of ground terrestrial ground terrestrial base stations in order to support many flying vehicles. Thank you very much for listening. If you have any questions, I would like to answer them.